Hi there, Luke McKinney, Prep 101's instructor for Physics 1D03. In this video, we'll look at the basics of circular motion and how those fit together with forces to give us a second class of forces problem based on all the same ideas as before.
Circular motion is when, as you'd expect, you got an object and it's going around and round in a circle. Now here's the thing about when an object's going at us around in a circle. At any one instant, it's just going in a straight line. Like this object here, it's going up right now. And when it's at the top, it's going around a circle clockwise, but at this instant, it's just going to the right. And we know that because, for example, if we are whipping around a little ball at the end of a string, if we suddenly let go of the string, then it stops going in a circle. It just flies off in a straight line. And that is the velocity at this point. Now, this straight line, if we look at it, only touches the circle once at this one point. And so that's called a tangent to the circle, just a line that only kisses the circle at one little point. At every point, it has this velocity. Now this velocity, if we look at it, it's a tangent to the circle. So it's at right angles to the connection to the center. And we see if we keep going, if we're here now, the velocity is pointing down. So the direction has changed. But remember, velocity is a vector. It has a size and a direction. So if the velocity has changed, what does that mean? If the velocity changes, that means there is an acceleration. Remember, in conversational English, we think of acceleration just as speeding up, but in physics, acceleration is speeding up, slowing down, or changing direction. And these objects are changing direction, and if we look at how it's changing direction, it was going up, now it's going to the right. So the change in direction is to the right. Then it was going to the right, now it's going down. So the change in direction is down, and so on around the circle. We see this acceleration is always towards the center of the circle. Center of circle. And that's why it's called sometimes centripetal acceleration. Literally means seeking the center. It's trying to get to the center. So you have the centripetal acceleration always towards the center of the circle. And that's given by the speed squared over the radius. I might say, hang on, Luke. V is for velocity. That's a vector. It's true, but when you square the velocity, it just becomes a number. Like 10 meters north times 10 meters north just becomes 100 meters squared, or 20 meters per second east times 20 meters per second east just becomes 400 meters squared per second squared. So it usually refers to speed here. In fact, I say speed because you'll often see questions dealing with this talk about speed in that equation. So you're always going to have this acceleration towards the center of the circle if you're going around in a circle. That's not the only acceleration you're having. That's acceleration because we're changing direction. But what if we're speeding up as well? What if we're going around in our circle and we're speeding up, we're getting faster? Well, that is called tangential acceleration because it's in the direction of that tangent line we saw. So you could have this object here. It could have a tangential acceleration, speeding up or slowing it down, and the centripetal acceleration, holding it into the center of a circle. And those are at right angles. And we've already dealt with stuff like that before. Very first thing we did in the course, we know if we have an x component and a y component of something, so if we had an x acceleration and a y acceleration, we can find the magnitude of the total acceleration by Pythagoras, the square root, sum of the squares of the other two sides. And that gives us the total acceleration. And the same is true here. If we have something going in a circle, so it has centripetal acceleration, that's just a fact. If it's going around in a circle, it has centripetal acceleration. And if it's speeding up or slowing down, so it has tangential acceleration, then we can find the size of that total acceleration the same way, by the square root, sum of the squares of the other two sides. And this is just something we can automatically do if we have those two things, the two different types of acceleration. Sometimes there's a couple of extra words they can give us dealing with this sort of thing. If we have an object going around in a circle, how long does it take to go around a complete circle? That's called the period, the time t. And the time to do anything, we know, is the distance over the speed. Well, the distance around a circle is the circumference, 2 pi r. And we have the speed of the object already. So now we see if we want the period, we need the speed and the radius. Or if they give us the period, we could rearrange that to find the speed we need at any time. Another word is the frequency. How many times does it go around every second? And that's just 1 over the period. Now we can see how that works. If the period is 0.2 seconds, it takes 0.2 seconds to go around a complete circle, then the frequency is 1 over 0.2, which is 5 hertz. So it'll go around the circle 5 times every second. We saw that the velocity was changing, and so that means there must be an acceleration, the circular acceleration, or, for its formal name for dates, the centripetal acceleration. And that leads us to the next connection. If there's an acceleration, there must be a total force causing that. Remember, the sum of all the external forces on something is equal to the mass by the acceleration. And that has led to two different types of problems so far. We saw the first type, the sum of all the forces are equal to 0 because the acceleration is 0 when something is in equilibrium. Or another word for that, constant velocity when the acceleration is 0. Another is when an object's just moving along like a block on a slope and we want to find the acceleration, or if we know the acceleration, to find some other force. So the sum of all the forces is the mass times the acceleration. And both of these problems are done the same way. You just draw the object and the force is acting on it. Let's say there might be weight, normal force, static friction, a classic. And then you apply the sum of the forces in x and y. Now, circular motion does exactly the same thing. It's just one more type of that. The sum of all the forces is the mass times the centripetal acceleration. So the sum of all the forces towards the center is the mass, speed squared over radius. And from that point on, you just work things out as before. Now, this is called the centripetal force sometimes. Sometimes people call it the centripetal force, or a little more relaxed, the circular force. Now, there's a key thing about this. This is not a new type of force. There's no such thing as an actual circular force that picks things up and spins them around in circles, because we don't live in Skyrim. There's no magic spells that can do that. This is just a measure of how big a force you'd need to hold something moving in a circle. And there's all sorts of examples of that. The most famous, you've got the Earth. Hello. writing the word Earth is so much easier than, drawing all the continents and stuff. And you have the moon, not to scale. Some people say the moon shouldn't have a capital M, but come on, if my hometown, tiny place, gets a capital, then so does the moon, is what I say. And in this case, we know it's the force of gravity that acts towards the center so that must equal the centripetal value. Or if you have a ball and you're whipping it around in a horizontal circle on the end of a rope, then the tension in that direction must equal the centripetal force. But let's look at our equation again. Remember, it's the sum of all the external forces is equal to the centripetal force term. So it doesn't have to be just one. It very often is, but there's other examples. For example, if you're going around on a Ferris wheel, so you're sitting there, here's you sitting, red because you're important, hooray. And so you have the weight acting down and the normal force with the seat that you're sitting on pushing up so that you don't fall down. And the center of the circle is below you. So the sum of all the forces in the y direction must be the centripetal force towards the center of the circle. So that's the centripetal force down towards the center of the circle. Remember, in physics, plus and minus are just directions. Plus y is up, minus is down. So the forces are plus the normal force up minus the weight down is equal to minus the centripetal term. And they're a very fun set of questions, definitely ones you'd want to practice before exams with that. You've got ones with gravity, with tension and ropes, with friction and normal forces, but they're all just the same force problems as you have before. You draw the free body diagram, the object with just the forces acting on it, and then just like before, the sum of all the forces is the mass by acceleration. We just remember now there's two special cases. If things are in equilibrium, it's equal to 0. And if it's moving in a circle, then it's moving towards the center of the circle with the centripetal force. So as we saw, that can be plus or minus now going down there. And that's a lovely set of problems there.
I hope that was useful. There's plenty more useful videos in the playlist and even more useful exam style practice and tips and all sorts of things in the prep sessions. So make sure you join the Prep 101 Facebook Study Hub. You'll find out about everything we're doing there when the prep sessions are on, and there's even sometimes free ones, so you don't want to miss those. Hope I'll see you there.